Hello everyone, welcome to research webinars. Today's webinar topic is focusing on the batch distillation modeling, optimization and control, past, present and future. This presentation begun by Dr. Urmila Diwekar from based in US. As you know, research webinar is all about focusing on the research developments, and today we are focusing on the batch distillation. I'm very happy to introduce Dr. Urmila Diwekar. Currently, she is the president of the Vishwamitra Research Institute based in USA. Let me give you a quick introduction of what's her background to all of you. She's, as I said, is president of the Scholastic Research Technologies and also the Vishwamitra Research Institute, a non-profit research organization that she founded in 2004 to pursue multidisciplinary research in the areas of optimization and uncertainty and computer design applied to energy, environment, and sustainability. From 2000 to 2004, she was a professor in the Department of Chemical Engineering, Bioengineering, and Industrial Engineering and in the Institute of Environmental Science and Policy at the University of Illinois in Chicago. Before that, she was also part of during the 1991 to 2002. She was on the faculty of the Carnegie Mellon University with early promotions to the both associate and the full professor level. In the chemical engineering, she has worked extensively in the areas of simulation, design, optimization, control, stochastic modeling, and synthesis of chemical processes. She has made major contribution to research on batch distillation, and this work is well recognized. She is author of more than 190 peer-reviewed research papers, 7 books, and 15 chapters, and has given over 400 presentations, seminars, and has chaired numerous sessions in the national and international meetings. In separation, she is well known for her pioneering work in batch distillation design, simulation, optimization, optimal control. She has published in terms of the more than peer-reviewed journals. She conducted 11 educational workshops on this topic. She has also published the first book on this topic as well. She is authoritative and first of its kind book, which is widely used all over the world. She is author of the comprehensive software package for batch distillation simulation, optimal design, and control called Multi-Batch DS, which is used in pharma and specialty chemical companies in the US, Europe, and Asia. She has also extended the new approach for optimal control. She developed from the batch distillation to batch crystallization. In the last 2 decades, she has worked on green separation processes, including new approaches to computer design, solvent selection, and solvent recycling, NOx removal process, controlling naturally occurring radioactive materials from the fracking and arsenal removal from the water. As you see, Dr. Urmila has specialist, well-recognized person in this batch distillation. I'm sure you find this presentation useful to you. If you have any questions on this topic, please feel free to post your questions in the question box. Dr. Urmila will address them appropriately at the end of the presentation. Okay. Let me quickly introduce about Technobase. As you know, research webinars is managed and owned by the Technobase. Technobase is based in Thailand, established in 2005. It is recognized as International Resource Center for Polymer Industries and Process Technologies. Our services are pretty much global. We offer training programs, conferences. We do organize trade shows. We organize webinars, publications, consulting. We also introduce the knowledge tests. Our business focus on both sides, on the polymer side and also non-polymer side. Okay, polymer side, for rubber, plastics, polyurethane, adhesives, and coatings. On the process side, we call the filtration, separation, water and membranes, energy environment, and also the chemical engineering and process technologies. I encourage you to visit our website, technobase.org, for more information on activities. Just give you a quick, additional information on the webinars. What you are joining today is a research webinar. We focus on the research developments and especially on the areas. But we also have know-how webinars. It's a purely educational platform. We also have technology webinars, which is focused on the commercial technology promotion by the technology suppliers. And we do have eminent personality webinars, which is focusing on the journey of well-experienced and well-respected professionals about their, their lessons learned and their experience, their total journey about them. And so we have 4 types of webinars, and I request all of you to look at these webinar websites. You may be interested in some other topics relevant to you. Okay. So let's get to today's topic on the batch distillation modeling, optimization and control, past, present, and future. I invite Dr. Urmila Diwekar to make a presentation. Let me ask her to share her screen. Yes.
Good morning. Sorry, I think for you, good evening, everybody. Thank you, Prem. The topic of my seminar, I'm going to talk about, in some ways, review of the area of batch distillation, modeling, optimal design, and control. Before starting, I just want to introduce a little bit about my organizations. I have 3 hats. I am an educator because I was a professor in 2 universities here, and I have a special arrangement with University of Illinois where I have PhD students, and I teach optimization when I feel like, in a sense, once a year or twice, or once alternative years. I am the president of Vishwamitra Research Institute, and Center for Uncertain Systems, Tools for Optimization and Management. I concentrated more on uncertainties because in some ways life is uncertain. And I was telling my husband, saying that I want to actually work on this, and he is a physician. So he told me, oh, there is nothing uncertain, because in life, everybody dies sometime. So then I showed him this cartoon saying that after death also, you don't know what you're going to get. This is, I think, in hell, and essentially there is a different probability of getting different punishment. So even after life also there would be uncertainty. And that's why I started a Center for Uncertain Systems, Tools for Optimization and Management, and Vishwamitra Research Institute. It's a non-profit research organization. I have postdoctoral fellows in Vishwamitra Research Institute, PhD students in the university, and we carry out research in various areas, algorithms, methods, and tools, mostly related to decision-making, optimization, control, and related to uncertainty as well as without uncertainty. As a chemical engineer, I also work in materials and molecular modeling. Energy, environment, and sustainability is one area where most of the research funding is, and it goes from traditional energy to renewable energy, as well as some of the environmentally benign processes, basically design, optimization, and control. Some part of manufacturing planning, and also is part of this thing. So if you look at batch distillation, manufacturing planning and management comes in there. And now recently I have been working on biomedical engineering also, mostly in the on the computers. So we don't have a lab or anything, but we have each one of my members will be working on computer related stuff in all these areas. I also have, I also have a profit-oriented organization called Stochastic Research Technologies. where we have different software products and multi-batch DS, which is a professional multi-batch distillation system for multiple column configuration, operating modes, fractions, and products. This is a software I developed, and Equinox Software Limited, India is actually markets it. They have developed an interface, and it's been used in Europe as well as India and United States. The other software is related to in vitro fertilization. It's a personalized treatment decision analysis tool for doctors, and so sensor placement software. This is the stochastic research technology. As I said, that we are doing the multi-batch DS with Equinox, and essentially they are marketing it. So this is overall 3 organizations where I come from. In case you're thinking my accent is not clear, which I cannot change anything, but I can slow down, or if you think I'm talking too fast. So let me know about that. So coming to today's topic. This is a topic, modeling, batch distillation, modeling, optimal design and control. What I'm going to do is how this area started. So it's more of a history, complete review of where the state of the art is currently, and what may you see in this area in the future, just projections of the future. If you want to reach me anytime, you can use my email address, Urmila, URMILA, at vri-custom.org. It's dash, it's not underscore. Okay. So, or you can send me email at urmila@uic.edu. That is also possible. You can send me email at any email addresses. Okay. So if you think about batch distillation, first question is that why batch distillation? And as a chemical engineer, you learn distillation, but most of the time it's concentrated on continuous distillation because one concentrates on large scale manufacturing. And large scale manufacturing, people do use continuous distillation. However, if you have specialty chemicals or pharmaceuticals or some of the food industries where quality becomes important and maybe the material is not in large quantities, then you use batch distillation. The advantage of batch distillation, well, this is a conventional distillation I'm showing, continuous distillation on the left side of the figure, and batch distillation, which is a conventional batch distillation on the right hand side. In continuous distillation, you have feed in the column and you are taking products from the top and bottom. The column operates at steady state. But in batch distillation and in conventional batch distillation, you have a reboiler at the bottom and you are taking out the products at the top. Obviously, since there is no steady state except at total reflux condition, this is an unsteady state batch distillation. Things change with time and you have to pay attention. It's a challenging thing that it changes with time, but it offers a lot of flexibility for batch distillation. And that is very useful, why many times people choose batch distillation or continuous distillation. So for example, here I'm showing 3-component mixture. In the 3-component mixture, if you want a pure component, then in continuous distillation, you have to use 2 columns, n-1 column. While in batch distillation, you can actually get 3 products by taking different cuts from the same column, different fractions per cut. As time goes by, the number 1 will be the first product, number 2 may be the second product, and whatever remaining may be the third product. Okay. So you need just 1 column to separate this mixture. The other flexibility is that in batch distillation, what happens is things are changing. So the product composition, if you keep the reflux constant, just like in continuous distillation, your product composition of the more volatile component keeps decreasing with time. If you want to keep the component constant, then you have to use variable reflux. But there is something in between, which is called optimal reflux. You can actually optimize the amount of material you can get per unit time, or you can optimize profitability. It's called optimal reflux. So there are different operating modes, which allows you to operate the column cost effectively and can get better profits. Batch distillation also offers, and this is something is generally not covered in normal chemical engineering curriculum, because, as I said, batch distillation is relegated to small portion of the curriculum. As I said, in conventional column here in figure A, you have a big reboiler and you're taking product at the top. You could have multiple fractions, as I said in the second figure B, you could have multiple cuts or multiple fractions. And in the figure 3, you can actually recycle the waste cut. This can optimize your operation. So if your pure product is 1, the second is can be a small recycled waste cut, which you can recycle back to the reboiler and take the third cut. This can optimize column better. You could actually invert the column, or what we call it as a stripper operation, batch stripper. Essentially here it is shown that the feed is from the top. You don't have to have the big vessel at the top, but what you can do is a liquid feed to the top of the column, take out the vapor from the top, condense it and go to the feed column. And you have a smaller reboiler in this column, not shown here, but essentially if you have heavy components which are important, then this is the operation to use rather than conventional. People use conventional batch column because that's how they have learned, but stripping is a very good operation if you have heavy components. If you have small heavy impurities, maybe it is better to remove them first, and that's where the stripping is useful, stripper column. Also, sometimes your heavy component is large as compared to the light component, and then small as compared to the light component, then also stripping is useful. There is another column called column with a middle vessel, which has stripping and rectifying section. And essentially, this is much flexible than continuous column. It looks like continuous stripping and rectifying section, but it has more flexibility. And you can, suppose I have 3 pure products I can take it in one column. Okay, you could have multiple vessels depending on this thing. So you can go on different configurations, and they are really useful. People do ask me whether I have seen implementation of this new column configuration in real practice. People have implemented stripping. Some of my industrial case studies, I'll show that. And middle vessel columns also, there are pilot plant implementations of that. Middle vessel and multi-vessel. And if you need information about that, I can send you the pictures of these columns. Okay. So this is why batch distillation is useful. Now let's go to where the real theoretical analysis started in this. The first analysis of batch distillation was done for simple distillation. Simple distillation where there are no plates, just a reboiler, and the things are boiling and you're taking out product at the top. Lord Rayleigh was the first person in 1902. He actually analyzed simple distillation, and what he said is that you can actually link the amount remaining in the bottom to how the composition is changing with Rayleigh equation. And here I am showing on the right hand side the Rayleigh equation. The relation between XD, which is the distillate, versus XP, which is the composition in the bottom, is actually equivalent to thermodynamic one theoretical stage. And we all have learned in distillation is that one theoretical stage is not sufficient to get the purity you want, and you want number of theoretical stages where you are mixing liquid and vapor coming up and liquid going down at each stage, or in packing, whatever it is. It's essentially number of thermodynamic theoretical stages should be more than one to get the purity. And that's the batch distillation column. Okay, so batch distillation column also, the Rayleigh equation is still applies, where you can link whatever is remaining in the bottom to the top composition and bottom composition, but the top composition and bottom composition is linked by many theoretical stages. Okay, so material balance on all the stages will link the XT, how XT is related to XP. Also, what is happening is that XT is changing with time, XP is changing with time. Okay, and that's why this is a differential equation and not a steady state algebraic equation. So what happened is that Rayleigh equation still applies, but I don't know how I will link XT to XB. So here in batch distillation, if you keep a reflux constant, what happens is that the more volatile component XT keeps on decreasing. So here the black line on the left-hand side figure is showing constant reflux, right-hand side, and T is the time in the bottom. You're seeing that XT, more volatile component, is decreasing. If you want to keep it constant, that is the blue line, then your reflux needs to change. It needs to increase with time. And so this is the condition. And then there is optimal reflux. If you look at the literature in batch distillation, okay, so Rayleigh equation was 1905, and then in 1925, we got McCabe-Thiele diagram. What McCabe-Thiele diagram said is that if you have a binary distillation graphically, I can link the distillate composition to the feed composition and bottom by theoretical number of stage and reflux ratio. Okay, as soon as the graphical integration technique was available, Bogart in 1937 said, okay, I can use Rayleigh equation and I can use a McCabe-Thiele diagram where I say that XT is my top composition, and instead of feed composition, I have the bottom composition, because that's how the feed is. And he gave equation method for variable reflux. In the variable reflux, XT is constant, so you can take the value of XT and draw a different reflux line. And as you say, reflux is increasing, and you can integrate Rayleigh equation. So that was the theoretical analysis of modeling variable reflux analysis, use Rayleigh equation and use McCabe-Thiele diagram. Constant reflux analysis came in 1940, similar to variable reflux analysis of Bogart. He said, I will use McCabe-Thiele diagram. Instead of keeping XT constant, I will be decreasing XT as the time goes and integrate Rayleigh equation. So that was the constant reflux analysis in 1940 for binary distillation. What happened then is that after 1937 to 1940, you will see that people have worked on variable reflux. After that, and constant reflux, but you will see that they also started working on optimal reflux. Okay, and so till 1940 to 1960, people stick to McCabe-Thiele diagram and also Rayleigh equation. And 1960, Hukaba and Danley said, okay, let me analyze the dynamics of batch distillation, because it's an unsteady state process. So essentially it involves writing differential equations for reboiler and for all the column, and then vapor liquid equations for the column. That's algebraic equation. He wrote down the equations, but in 1969, when Di Stefano is the person who analyzed it, saying that, well, these are differential equations, but they are difficult differential algebraic systems as compared to continuous distillation, because in batch distillation, I have a big reboiler, so I have a lot of material in the reboiler, while on the plates, holdups are very small. Okay, so there is a time, the time constants are so varying that you need, it becomes a stiff differential equation system. It's a difficult equation system to integrate. And he also gave this thing saying that what is the stiffness factor? It depends on K, which is the equilibrium constant, V is the vapor rate, L is the liquid rate, and H is the holdup. L plus KB by H. If it is very large, you have a stiff differential equation system, and that's generally the case in batch distillation. And he said that if you also include energy balance, then this system will be difficult to integrate. So he suggested that instead of differential equations, use difference equation for energy balance. And most of the software packages to date actually follow the Stefano model, which is multifrac TS, multifracs, also Aspen's package, as well as ChemCat's package. ChemCat's package actually doesn't give stiff numerical integration, so they face problems much more than Aspen's package or any other package like multi-batch TS. And this is the regress model, where you write down differential equations, differential material balance equations for each plate and reboiler and condenser, and write down difference equations for energy balance and VLE. Okay. What happens if you don't use stiff differential equation? That you will see here that L plus KV by H is the ratio. I'm taking a really large holdup, saying 10% holdup on plates, and you will see that this is a three component system, and you will see that on the left hand side you will get smooth profiles and distillate composition between 0 to 1, while if you use non-stiff integrator, you get actually negative composition. This can happen in ChemCat's model because they don't use stiff differential equation. But even for stiff integrator, this can happen if L plus KV by H factor is very high. So here it is 1% holdup. You will see that Aspen's model as well as ChemCat's model will not be integrating it. It's giving negative composition, or it's just saying that I cannot integrate it. And that's where you need a model change. And here what we proposed is to take care of the problems. You have another model, also what is called semi-regress. Actually, it is a regress model, but just called as semi-regress. And instead of using differential material balance on the plates, you use material balance equations. Since your holdups are small, essentially you are reaching instantaneous material balance on these things. And they are not different, the results will not be different, okay? And so essentially we have this model. These models are good, but the thing happens, so this is developed in 1988, and if you look at literature on batch distillation, Doherty and co-workers have really added a lot of research papers in this area, and they actually use this kind of model. They worked on azeotropic systems, and I'll come back to that. So that was the thing. Then in 1998, it developed a shortcut method because what happens is that if you have to define a column from scratch, if I have a mixture I want to separate and I have a column I want to use, and I will be saying that, okay, I want this purity. many times your column may not be able to give you that purity because you are not feasible region of operation. And that's where shortcut methods are useful. I developed this shortcut based on the assumption that continuous batch distillation can be considered as continuous distillation with changing feed. We changed the equations for the Finsky-Underwood equations for continuous distillation to batch distillation, and essentially instead of we use Rayleigh equation or differential material balance equation for the boiler, and FUG and HG equation for others. So it's only involves one differential equation, sorry, n+1 number of components plus one differential equations, but only 3 algebraic equations to solve the problem. And essentially it's very fast, but its main thing is that it identifies feasible region of operation. For design optimization, this is very useful because you may be simulating the columns, but your column may not be the right height or right number of plates or right reflux ratio, and you will be just not knowing that. Okay, essentially this is useful design optimization synthesis, came in 1988. If you look at optimization of batch column, and if you look at optimization literature as such, optimization literature in Western scientific world, they identify the first optimization problem as proposed in 1000 BC by Queen Dido. Queen Dido was in Africa, and she was a queen of Carthage, a city near a sea, and she wanted to build an arena, okay, arena for games. And she said that I have this rope made of hide of bull. If you can build an arena where the length of the wall is same as the length of this rope, but it should cover maximum area. So that was the maximum area isoperimetric problem. And this problem actually, if you look at it, is an optimal control problem, how the rope will move. So it's a vector decision problem, optimal control problem. And first systematic theory of optimization was also developed for optimal control problem in 1694. If you look at batch distillation literature, many of the early optimization problem concentrated on optimal control. Okay, many of them are done for actually for binary distillation, and initially people were really this thing saying that, okay, what is optimal control problem? Optimal control means you can, it's the same, it's not the same as feedback control, but you have to decide the trajectory in inputs. So the common optimal control problem you will see is traveling in the airplane. How to decide going from one place to other by airplane is they decide the trajectory in advance based on minimum time required, and that's trajectory optimization, that's the optimal control problem. In batch distillation, that involves changing reflux with time, okay? And so most optimal control problems were solved before any other optimization problem in batch distillation, and essentially to date also it's a very popular area of research. Design optimization, just like constant reflux, variable reflux came up later, and it still continues, but not as popular as optimal control problem. What are the optimal control problem? So the maximum distillate problem, which is where the amount of distillate of a specified concentration for a specified time is maximized. So fix the batch time and say that I want to maximize the amount of distillate of this purity on average purity, okay? And there were I haven't included everybody's name here, but there were a lot of people who worked on this. Minimum time problem, saying that, okay, I can fix the total amount what I want of specified purity, but I want to minimize batch time. There were different people worked on this problem. Again, I haven't included all of them here, but started in 1960, continues to date. And maximum profit problem is a combination of both, saying that I want to maximize this select minimize batch time with a profit function. And this function varies from just including material material area of profit, saying that as well as sometime cost of heating, as well as capital cost. Okay, but in general, capital cost consideration in batch distillation is not important, but there are different profit problems. So the problems in optimal control people they handle different: maximum distillate, minimum time, maximum profit. They also actually concentrated on different methods: calculus of variation, dynamic programming, maximum principle. Initially, they were curious about the methods, so they tried to solve the same problem with different methods, and then as computers become prevalent, more methods came up. Okay, so the literature in optimization, you can divide, saying that different methods and different types of optimal control problem and optimization problem. We also, there are areas where we have something for control. Suppose you have a large column, then there are modeling of that column, especially for control using reduced order model. That also came in 1988. Now, the thing happens is that most important area in batch distillation, which is also useful for continuous distillation, is the work by Doherty and co-workers from 1981 to late 90s. They worked on azeotropic distillation and what we call as residue curve map. Doherty and workers said that if residue curve maps is same as Rayleigh equation, is same as how simple distillation behaves for different azeotropic systems. Azeotropic systems, as we know, actually, if you look at binary azeotrop, it provides barrier in between. So in barrier, at the one point, but if you have 3 components, then there could be many azeotrops, binary azeotrops, ternary azeotrops, and what they call it residue curve maps, how the simple distillation is behaving. And what Doherty and co-workers propose is that by looking at this simple distillation behavior or residue curve map, you can actually predict what can happen or how many columns, continuous columns are required, how many fractions, how the cuts in batch distillation required, whether you want to add an extractive agent, how you add an extractive agent, how you add a solvent is a function of residue curve map. And that was very, very useful and essentially covered the area of both continuous and batch distillation. A lot of people have worked in this area, and essentially this is useful, as I said, to decide even what solvents can be used. Okay, so these are complex systems. These are azeotropic systems. The other thing is that complex columns. Complex columns can be, I talked about the stripper, that is the inverted column. Most of the work was done in late 90s. It still continues, but it's in original work in that area. Middle vessel column from 1982 onwards, and multi-vessel column. Okay, so what is conventional column? Conventional column has a reboiler at the bottom, and you take out the product at the top. In inverted column, you have the reboiler giving feed at the top and taking out the product at the bottom. Okay, as I said, it's very, very useful for if your heavy product is important, or if you have small heavy impurities you want to remove, or so this column is better than using batch distillation, conventional batch column or rectifier. So this is the stripper on the left hand side and convention column on the right hand side. Okay, you can see the difference. Middle vessel column, you could have a vessel which is actually coordinating the flows from on the top of the column and on the bottom of the column. You have rectifying and purification, and the products are in all three vessels: reboiler, condenser, and middle vessel. In multi-vessel column, you have different vessels for feed, and you have different columns connected by it, and essentially take out the product in every vessel. So if you have 4 components, then instead of middle vessel, you should have 2 vessels in the middle. These are the proposed column, and in multi-vessel column, you can even operate at total reflux to get the pure products. You don't have to start taking out the product and then make taking out reflux or reboil ratio. Okay, so these are the columns which came up, as I said earlier, in late 90s, and some of them have been implemented in real practice, and some of them have been implemented in pilot plant. What happens after 2000 onwards, the recent area are, again, if you look at it, many of the papers are on the optimal control. Deterministic optimal control, maximum distillate, minimum time, maximum profit problem, and also nonlinear control. Okay, so those are this thing. Also, in recent years, my group has worked on what happens when feed composition changes. Because in batch column, you don't get the same feed composition all the time. Can you do a robust operation? Many times you don't know the impurities, and those cause uncertainties. Can you do that? So we worked on that, and this is stochastic optimal control. In recent development in complex systems, you will see that the group in Germany have worked on how do you select entrainers for stripping as well as rectifying sections or of batch column. Okay, they have given heuristics. It's a very nice work, and we actually use a computer-aided design and concept of residue curve map to design the solvents, for batch column. Okay, so those are the things which came up in the complex systems, and then also some work on reactive distillation. Again, the concept of residue curve maps have been used for reactive distillation area, but only equilibrium reactions were considered, and Maccabe-Thiele diagram. And it's again some nice work on reactive distillation. What is continuing is, as I said, that lot of work in optimal control is continuing now, and also inverted columns, middle vessel columns, synthesis of complex columns. So many papers have come out in the literature in the recent years. Very recently, in 2020 and 2021, my group worked with Firmenich in Firmenich, Switzerland, where they had a system. Here I'm showing GC, which is gas chromatographic gas diagram for components, and they could only identify 6 components out of 10. So essentially 4 components where only boiling points were known, and their mixture also the varies, the feed composition varies. So we actually developed a method for handling that kind of thing called, and it's published in INEC research in 2020. It's called problem of missing components, and divided wall batch column. Also, you can see that divided wall batch column is also very useful, just like middle vessel column. And this is extension of continuous column divided wall, the continuous divided wall column. Okay, and things are continuing in this area. Now, if you look at the software in batch distillation, I actually put here some requirement. For one thing is what we learned from literature. As I said that most of the batch distillation work, simulation modeling control is most of the columns are generally used in industries like specialty chemicals, pharmaceutical, as well as maybe food industry. And you will see that many times people don't know people don't have thermodynamic data, and so it is very essential for any software to have ability to generate data from structures. Okay, it is important to capture the operating flexibility of batch column, and so you need different operating condition. Also, as I shown, some of the models, rigorous model, fail, and that can happen if you have wide boiling component, low hold-up column, or flow rates are high, and you need hierarchy of model. You also need emerging columns like stripping, rectifying, and all. So in my book, I had compared different softwares, ChemCAD and Aspen Plus, as well as my software, Multi-Batch DS. You can see that the data bank from structures are possible in most of the packages, including ours. As far as operation is concerned, most of them talk about constant reflux operation. Some AspenTech has variable reflux, but not really the optimal reflux operation. If they only have the rigorous model and it fails many times, they don't have hierarchy of model. They don't have shortcut model for feasibility. Configuration is only rectifier, most of them, and don't have design feasibility or optimization. AspenTech allows optimization, but it's very complicated to implement. The other thing, because we have different kinds of model, the computational efficiency is also high in multi-batch DS. We have things like uncertainty analysis, which is actually if your feed composition is changing, it's good to use that to see whether your design or simulation is okay. So this is the comparison, and it is from my book, which second edition came out in 2012. So I will summarize and show you, if I have time, I can show you some of the case studies, the industrial case studies, but it depends on the organization. So I'll ask Param. So in summary, what I have shown is that if you look at batch distillation literature, batch distillation is an unsteady state operation. So Rayleigh equation was the first equation to differential equation to describe, but it is causes a numerical integration problems because batch distillation is more hard than continuous distillation to integrate because of big reboiler and smaller hold up on the plates. It may need multiple models, so people have proposed multiple models. There are multiple operating modes: constant reflux, variable reflux, optimal reflux. So the literature is describing some of this, and most of the optimization work was concentrated on optimal reflux. And then recently, different configurations of batch distillation have been proposed, not very recently, but in late 90s and early 2000. And they are very useful. And the software-wise multi-batch DS, since it is based on over the year, all the research work, it captures this flexibility in multiple columns, operating modes, and configuration. So, and models. Prem, do we have time to show some industrial case studies, or if not, I can
Yes,
start.
that would be nice if you can show some industrial cases. Please go ahead.
So
Yeah.
the thing is that these are the case studies which was done in multi-batch DS. So I'll show you. People ask me that optimal reflux changing reflux, has it been implemented in real practice? There are examples, and I'm going to give you this example. Before that, I am just going to say that this is where you will see a lot of future work, new column configurations, reactive batch distillation synthesis, control, and uncertainty and flexibility analysis. So this is the industrial case study 0, because before multi-batch TS, what's called multi-batch TS, this was done there. And this is coming from Upjohn Pharmaceuticals that time. Now it is Pfizer. And they actually implemented optimal reflux in their column, and they could get 40% more profit. Okay, so they had to get some sophisticated controllers, but they felt that the investment gave them a big payoff, so they did invest in that. So it has been implemented in this thing. The second case study is coming from Mexico, Conatus, Mexico. They had, and I'm not going to get into the details of their system, but they had a 3-component system. Component 2 and 3 were close boiling. And essentially their component 3 was their important product. Component 2 was the second important product. And they wanted a design, and what we found out is that the rectifier actually, if you do it, because they have a heavy component which is important, and 2 and 3 were close boiling, it needed something like 70 theoretical stages, and the product they got was something like 35% of the feed. When we said that they can change the configuration and use the stripper, they actually needed a very small column compared to the 70 plate column. They only needed 20 theoretical plate column, and they got 46% of the product, more product than before, especially the bottom product. And so the stripper was a better operation. Okay, this is Conatus, Mexico. So they have heavy product, and they also needed less amount of time. For 70 plates and this thing, they needed 5 hours versus 3 hours of stripping. So essentially they had a big profitability margin. What we found out is that they needed less reboiler duty also because of the time, as well as the small reboiler in the stripper. Okay. Third case study, which is a case I called 0, 1, and 2. This is from Mallinckrodt Chemicals in United States. They had a peptide product, and they had acetonitrile water mixture. And what was happening is that the current azeotropic agents, if you look at what extractive agent they were suggesting, environmentally harmful things like benzene as azeotropic agent. Their point was they had a lot of acetonitrile, they had, and they needed to separate a lot of acetonitrile, and they needed to separate water because the water couldn't be just dumped, okay? And they should get acetonitrile. So what we did is we actually suggested saying that computer-aided molecular design, what solvent to be used using the residue curve map technology. We suggested that they can have propylamine or acetone as a solvent, and essentially they can get pure water, which is much by using stripping, and then they can add solvent and get pure acetonitrile. Okay, so this is the residue curve map analysis. So if you look at it, you essentially have batch-wise addition of in the environmentally benign solvent, which is propylamine up here, and you change the feed point so that you cross the boundaries and get to more propylamine and this thing. So we suggested they use either stripper or middle vessel column, and in middle vessel was more profitable. You essentially take out first water, then in the first fraction water is coming out at the bottom, then you get the solvent at the top and acetonitrile water mixture, and then acetonitrile and solvent at the pure. In the same pre-cut you can get this. They didn't implement middle vessel column, but they implemented the stripper, and they did a better operation than the rectifier. This is actually Pfizer India. We suggested this thing. They had ethyl acetate THF water system, and they wanted THF to be 95% pure, as well as they wanted more than 80% purity for ethyl acetate. And right now they are using 3 fractions. Okay, the first fraction, second fraction is the waste fraction, and third fraction is they needed 15 hours of 18 hours for first fraction in batch. Right now 16 hours in second fraction and 15 hours. So they are spending 49 hours of total time to do this distillation now. What we proposed is middle vessel column. If you look at the product, they were getting 7,295. This is just, I have camouflage things here. So per batch, and 5,000 kgs of the other product. What we suggested is actually use middle vessel column. Instead of 49 hours, they can get 4.8 hours of batch time, which is order of magnitude reduction in batch time, means profitability, and they get more THF. That instead of 7,000, you get 10,000 kgs of THF, and ethyl acetate is less. Instead of 5,000, we get 4,000, but their main product is THF. So this is what the proposed configuration. Then they had Harmony India. They had 6 components, and they had 2 large columns to separate out the product. This is a continuous column. And what we suggested is a stripper batch column. Instead of a large column of 57 trays, they needed 20 trays. And essentially you get same purity in batch column, which is a stripper. These are the proposed column. So this is thing. Then so this is the these are some of the industrial examples. In most of these cases, what you will see is that we saved a lot of energy also, and that really helped. So you could use different configuration, different column. If you want to see the demo of multi-batch DS anytime, contact me. I can show you the demo. Feel free to contact this thing. So we have a commercial and also educational version of multi-batch DS. With this, I want to stop here and answer any questions. Thank you.
Thank you very much, Dr. Urmila. Okay, we have some questions here from participants. Let me show you on the screen.
Okay. Actually, when they talk about differential distillation, they do talk about simple distillation, which is a batch distillation, but not that many plates.
Okay.
Okay. What kind of process problems we may experience when we are handling difficult fluids? So difficult fluids in a sense of, if you have azeotropic systems, that becomes difficult systems. So one of the things is that you have to choose the configuration as well as the separating agent like solvents, extractive solvents and things very properly. So otherwise you may get into difficulty that even if you have a large column, large reflux and things, you may not get the purity you want.
And guys, you can post any questions you have, please. Okay, oh my God, okay.
Okay, mass transfer efficiency and tray efficiency. Okay, the thing happens is that most of the models in literature as well as in the software in batch distillation, they don't consider tray efficiency as inherent in the model. They implement it separately because you have to write differential equations for theoretical stages. So it operates as similar to continuous distillation, and there is a efficiency package which actually for your column will just calculate the efficiency and iterate on it, but it's not inherent in the model itself. Okay, yes, it is available through Equinox, and the cost is something they determine. It depends on whether you want commercial version or the educational version. I'm sorry I cannot address about what the cost is, but it's not very expensive. That's the only thing I can say. You know. And I handle the technical area, the economics is they handle. So you can send me email or to them and they will give you the pricing. And if you need to see the demo, feel free to contact me. I can arrange a Zoom meeting and show you the demo anytime. That is independent of whether you're buying or not buying. Okay, how do you calculate azeotropic pot capacity if the reaction is at reflux condition in a batch reactor? Actually, I didn't understand this thing, but let me see if I can answer it. What from my understanding, you can by simulation. Okay. Also, you can do the residue curve map, which is just doing the simple distillation calculations. You can find that. If you want more detailed answer, just send me email and I'll try to connect with you separately.
Okay, that's all the questions I received. Okay, Dr. Urmila, thank you very much for answering all the questions. Excellent presentation. Thank you very much. Would you like to give final remarks before we end the webinar to the audience?
Pardon, my final remarks are feel free to contact me anytime with any questions you have. I like challenges. So if you have something where things are not working, we can look at it together. Okay, thank you very much. And my email address and things will be shared, I guess, right?
Yes, that's right. Yeah.
So,
and this presentation we can share to the audience as well. That's correct.
I checked with Equinox. They said wait on that. So.
Okay, that's fine. I will ask them any questions they have. They can pass to you. Yeah. So yeah. Okay, that's the end of the webinar. I'm hoping it's useful to you guys. If you have any comments, suggestions, or feedback on this webinar, appreciate your feedback. Dr. Urmila, thank you very much for doing excellent presentation today. And guys, I had to stop the webinar here. Please check our website, research-webinars.com for up-to-date information. I'm hoping to invite you in future webinars. Thank you all. Bye-bye for now.
Thanks. Thanks.